Today we want to talk about Lagrange multipliers, and we introduced the idea of this problem last time. The goal is to optimize a function subject to a constraint. First line typo is always a bad sign. We want to optimize some function subject to a constraint. The function f of x I will refer to as the objective function. And in this case, the g of xy equals k. This is a constraint. When we talk about optimizing a function, we want to find a maximum or minimum, but we needed one word for that. So the example I think I gave last time, which is the example that I always give, I don't actually remember this, I'm just making this up, but minimize the surface area of a cylinder containing a fixed volume. Our objective is to minimize the surface area. That would be our objective, the surface area function, subject to a fixed volume. I would put the volume function for G, and I would state K as the fixed volume. Then we actually solve that problem and realize that no can is shaped that way, because it ends up being about as tall as it is wide. The diameter and the height are about the same because it's trying to be a sphere. So that's the idea. We want to try to maximize or minimize some function subject to some constraint. We want to optimize the function f of x, y. So that means we're going to be taking derivatives, set it equal to 0, and solve. But now we're going to add to that. We're not just going to look for maximum and minimum values of the function itself, specifically because we might be dealing with a function that doesn't have a maximum or minimum value, like the surface area of a cylinder. We can get a minimum surface area of 0 by making it height and radius 0, but then we're not containing any volume, so that's not useful. So we're going to take derivative set equal to 0 and solve, and add some additional information to it. Here's the cool part. Instead of just taking derivative set it equal to 0 and solve, find out where the function flattens out, I say make these go in the same direction. That's it. This is what we're trying to solve. Instead of gradient of f equals 0, I want the gradient of f to equal some constant times the gradient of g. And then make sure that this is subject to g of xy equals k. So with f of xy, with a function of two variables, f of xy and g of xy, the gradient of f equal lambda times the gradient of g is going to be two equations with x and y. And then we have a third variable. We've got that lambda as a third variable. And so we need the third equation, and there it is, the constraint, g of xy is equal to k. So this is going to produce a system of three equations in three unknowns. So this is a description of a system of three equations in three unknowns. Fx equals lambda gx, Fy equals lambda gy, and g equals k. Those are your three equations. Your three unknowns are x, y, and lambda. Lambda is a constant, and that is the Lagrange multiplier. So let's take a look at what that equation is asking us to look for. So I want the gradient of f to be lambda times the gradient of g. Lambda, the Lagrange multiplier, is a constant. I'm going to keep saying constant. I'm going to keep meaning scalar. The reason I want to bring up scalar is that gradient of f and gradient of g are both vectors. So when we write the vector equation, gradient of f equals lambda times the gradient of g, we are looking for a place where the two gradients are pointed in the same direction. The direction of maximum increase is in the same direction. Lambda just indicates the scale. Maybe gradient of f is longer than gradient of g. Maybe gradient of f is shorter than gradient of g. What we want is these two vectors to be pointed in the same direction. We're looking for a place where the gradients are pointed in the same direction. The direction of maximum increase for both the objective and the constraint is the same. We're looking for where the direction of maximum increase for both functions is the same. The lambda does have meaning, but the most important part is that the vectors are pointed in the same direction. We can interpret this, since the gradients are perpendicular to our contours, we're looking for where the contours are tangent to each other. If the gradients point in the same direction, then the tangents are also pointed in the same direction. So we're still looking for where a tangent We're still looking at the tangent. We just want the tangent of our objective and the tangent of our constraint to be the same. We want the objective and the constraint to be pointed in the same direction. I usually draw this picture, even though the gradient of each function is pointed in opposite directions. Opposite directions is same directions in terms of vectors. The lambda is just negative. Left and right aren't different. Left equals -1 times right. Same direction in terms of vectors. But at this point, these two gradients are pointed in the same direction. And that means the tangents will be in the same direction as well. So the two functions are tangent to each other. The objective and the constraint are tangents to each other. This is just an evolution of what we were doing before when we take the first derivative, set it equal to 0 and solve. We're looking for where the function was flat because that's where the function is changing direction. So we were looking for where the tangent was equal to 0. Here, we're just looking for the tangent of the objective to be going in the same direction as the tangent of the constraint. The objective and the constraint are traveling in the same direction. They're tangent to each other. That means their gradients are going to be pointing in the same direction, which is colloquially, the gradients are scalar multiples of each other. This happens to be tangents with, I drew this horizontal, which was a mistake, but this could happen at all kinds of wacky angles. So, yeah. So erase what you just copied, draw it this way, and then we can move on. I'll wait. I'm just kidding. I'm not going to wait for you to redraw this. Any questions? We could look at this gradient of f equals lambda times gradient of g, and g is equal to k, as just some system to solve. But we want to recognize where this comes from. I want you to see that gradient of f equals lambda times gradient of g, as you want these vectors to be pointed in the same direction. At the very most, opposite direction. We're just scaling the direction. How's everybody okay? Mechanically, the instructions for solving a problem mechanically just become like the more common instructions. The more math classes you do, instead of learning some particular technique, it's just like, oh, here's what you want, now make it work. Everybody remember partial fraction decomposition? Partial fraction decomposition is where you break up break up a rational function where the denominators of the sum are factors of your original denominator. Ultimately, the instruction for partial fraction decomposition is figure out the sum that you want. Now make that work. Just make that happen. And and more math that you do, a lot of times like, oh, this is what you want. Now we need to go make that happen. Part of the reason is we spend a lot of time doing things like solving linear systems, finding where two lines cross, or if those two lines are parallel, or if they're secretly the same line. That's the MCU version. You see, we're the same, you and I. Probably like Superman and Lex Luthor. Superman's all indestructible and strong, and his nemesis is just some dude that is smart and rich. I can't punch a moon. Well, see, Batman is just a dude that trains a lot. Batman is just like a superhero gym bro. Yeah, he's smart, rich, and trained. Lex Luthor is like, oh, I'm not going to do that myself. That's what minions are for, Batman. And you had one, and you got all tore up when you got killed. So you're supposed to be heartless towards your minions. Lex Luthor would be like, oh, Bruce, you don't know how to treat your underlings. Anyway, what are we talking about? All right. So we spend a lot of time solving linear systems, but we don't spend a lot of time solving nonlinear systems because we can't categorize that. There's linear systems where you have like the substitution method, the elimination method, solving with a matrix, Kramer's rule of all things. But once it becomes a nonlinear system, it's like, oh, make it happen. And you just have to know how stuff works. Here's a typical example. I think I'm lifting this one directly from, it's where your two variables are in a product and the sum of their exponents is equal to 1. It's popular because it shows up in business applications. Now, if I want to minimize this function or minimize this function, I'll just make x and y equal to 0. And if I want to maximize this function, I just make x equal to infinity and just make y non-zero. And then we're done, right? So we need to be subject to some constraint. That's exclamation points. A typical example. I'm just going to use the one from the book because it struck me as so funny. This is an example that shows up in like a business application. I think that's the classic one. This is the form of this function has a name, which escapes me right now because it's Tuesday and we haven't had math for 4 days. So I haven't had math for 4 days. So I cannot remember the name. It's like a job something. Name for dude who said, hey, all this business stuff could use some more math. And so they mathed it up a little bit. But it's going to be our production with, let's say, labor and equipment. So X represents units of labor, Y represents units of equipment. This is how they interact, how we came up with these exponents. Step 3, profit. That's it. That someone decided that this is how it works. And that's why you all had different ones. Some of you had a x to the 0.2 and a y to the 0.8. Some of you had a 0.3 and a 0.7. Remember that problem that had that weird, those things where the exponent should be between 0 and 1? And it's like, oh no, it has to be exactly the ones that we picked. And it's like, oh, why is that? And why they was like, oh, because we don't understand the problem and we're just going with what the grad student said. But we can't just spend an infinite amount of dollars on labor or an infinite amount of dollars on equipment. We're going to have some kind of restriction. In this case, we have chosen 3.84. That's going to be like our budget. And even though 3.84 is super weird, we got this decimal, and these are going to be represented with fractions. We decided that this problem, P1 and P2, will have equal costs, which actually makes sense for me to make P1 and P2 equal. So. Then they're like, oh, let's use this funky 3.84, even though like 4 is like right there. 4, just go 4. I'm like, oh, no, 3.84. It's like, oh, why are you using decimals there and then like fractions here? Because we wanted thirds over there and they don't come out to nice fractions. Then use something else. You're like 0.6 and 0.4. Like, I'm up, fractions, decimals. All right. What's your messed up values of P1 and P2? They're going to be the same. I got to admit, I love this problem for all this weirdness. So let's P1 and P2 to equal 1. So our constraint is just x plus y is equal to 3.84. This is actually perfect for what we want to do. And with P1 and P2 being equal, it's much easier to draw this by hand, which I think is the real reason that we have this problem. Now, if we think about what our objective is, this is going to be a surface. This represents a surface. So we have this surface, x to the 2/3 and y to the 1/3. We could see that as x and y get close to 0, we'll be headed towards 0. And then as x and y increase, we'll be increasing. If we think about the form of this function, if we think about the contours of this function, there's a power of x and a power of y. They're inversely proportional. So we're going to get kind of this 1 over x shaped contour. So if we're just imagining the contours, so these contours will have to form x to the 2/3 times y to the 1/3 equals some constant. So if we just kind of pull those aside. So if we solve for y to the 1, we'll have y to the 1/3. We can see that y and x are going to be kind of inversely proportional. As x increases, y is going to decrease. And as x decreases, y is going to increase. And that's why we're getting this kind of y equals 1 over x shape. If you cube everything, we'll have some constant over, cube over x squared. So that's why all my graphs look like a 1 over x squared. A cubed over x squared to solve entirely in y. The important thing is that I wanted to see that y was inversely proportional to the square of x. What we're looking for is where which one of these contours is going to be tangent to the line x plus y equals 3.84. Our constraint is going to be x plus y is equal to 3.84. So we know what the line x plus y equals some constant looks like. X plus y equals 3.84 is going to start off at 3.84. And have a slope of -1. And we are looking for where the gradient of the objective is tangent to the gradient, or the gradient of the objective and the gradient of the constraint are pointed in the same direction. So let's get into the mechanics. The mechanics are going to give us a nonlinear system. So we're not going to be able to use some technique that we learned in algebra, even though they told us that we'd be using all those techniques in algebra and calculus. We're in calculus now, and we're going to be ignoring those techniques. Because the elimination method, which is going to be our favorite, is not going to serve us here because it's going to be a nonlinear system. Substitution is always in play, so I guess there's that. Let's find the gradient of f. The gradient of f is the partial with respect to x in the I direction, and the partial with respect to y in the j direction. Our gradient of g, since we've chosen P1 and P2 to be 1, is just going to be 1 I plus 1 j. We want the gradient of f to equal lambda times the gradient of g. This results in two equations. So when we write gradient f is equal to lambda times gradient of g, we get two equations. We get that 2/3 x to the minus 1/3 y to the 1/3 is equal to 1, or lambda times 1. We also get the j components, multiples of each other. This is two equations with 3 unknowns. Still too many solutions, but we also have x plus y equals 1. There's our third equation. Oh, x plus y equals 3.84. There's the system of equations and our Lagrange multipliers. So we can't use elimination. We can't set up a matrix. Cramer's rule. That's right. But we can't use substitution. Substitution is the most general rule and the only one you really needed from your algebra class. Notice that this first equation says lambda equals 2/3 x to the 1/3 negative 1/3 times y to the 1/3. And the second equation has another lambda in it. So I'm going to combine those two equations. I'm going to substitute the first equation into the second equation. Actually, let me reverse that. I'm going to substitute the second equation into the first equation, and it'll look like this. Oh, I said I was going to do the second into the first, and I did the first into the second anyway. So we can see the important part here. There's going to be a 2 left behind. We can multiply out the 3. That's not going to be the important part. What we're going to get is the ratio of our original exponents. This is why we wanted them to add up to 1. I don't know if this is really how business stuff works, or if this was set up this way because it makes it easier for like the business majors. Because notice that when they add up to 1, we can just kind of like easily multiply them. I'm just kidding, business majors. Don't at me. So sensitive. So I'm going to multiply by 3. I can get rid of that. I'm going to have a 2. I'm going to multiply by y to the 2/3. So I'm going to get a y over here. And I'll multiply by x to the 1/3. And that'll cancel this one out and leave an x over here. X to the first. Now we can see the ratio of y to x. And we can plug that into our other equation. Oops. Although I spelled 3 wrong. And whatever 384 divided by 3 is. Hey Siri, what's 3.84 divided by 3?
The answer is 1.28.
I got stuck on the 84. The 81 is sitting right there. Siri's like rolling her eyes at me. I don't know if Siri has eyes. She's rolling her camera head. Dude, 84. It's an 81. That's a 27 and one more. That's a 28. Come on, man. Hey Siri. What's 3.84 minus 1.28?
3.84 minus 1.28 is 2.56.
Thank you, Siri.
My pleasure.
She's embarrassed. So mechanically, we had to set up the system that we wanted. It ended up being a nonlinear system. Then we just had to do some stuff. For the most part, since we're setting up the equation gradient of f equals lambda times gradient of g, solving for lambda is going to be super effective. Solving for lambda and plugging it into the other place where lambda appears. That's going to be super effective, but it's not necessarily going to result in something as simple as 2y is equal to x. Incidentally, in case you're wondering, this is why 2/3 and 1/3. So this would happen. That's all. Because we wanted two things that added up to 1 to fit the form of the function. And we wanted the ratio of those to be 2. 2/3 and 1/3. 3.84, I guess they wanted something divisible by 3, but not obviously divisible by 3. Even though it is kind of obviously divisible by 3, I just failed to obviously divide it by 3. Right now, Hughes Howard's like, oh, come on, man, we threw you a softball. And you dropped it. Any questions? Comment. I'm gonna post chapter 15 for the Sunday after the 19th, whatever number that is. So, as usual, you're still gonna be able to continue them after that. And we'll try to get back onto our do stuff for Sunday schedule. That's gonna do it for today. That's gonna do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.